Hi. Recently, I was on Wikipedia because I wanted to find a way to generate random numbers given a distribution. And I realised it's quite a tricky problem because there are some distributions which you can generate random numbers from quite easily. So for example, uniform distributions and normal distributions. But let's say I wanted to generate random samples from a log normal distribution. This is a lot more tricky. And so during my research into this, I found this thing called the inverse transform sampling. So what the inverse transform sampling does, it takes uniformly distributed random numbers, so for example numbers generated between 0 and 1, and generates random numbers based on a distribution. So what does this mean? So if, for example, you had this, so you had this distribution here, so this is the cumulative density function of a distribution. If you generate uniformly distributed numbers between 0 and 1 on the y-axis, and for every one of those numbers, you use this cumulative density function or cumulative distribution function, you follow where that particular value of y intersects with the curve of the CDF, and then you follow down to the x value. And this generates non-uniformly distributed numbers based upon this distribution. So for example, this distribution has a higher probability density towards 0 and a lower probability density towards infinity. And you'll see that these uniformly distributed numbers became non-uniformly distributed with a tendency to stick around the 0. Now that's quite useful because it means that we can generate random numbers according to any distribution as long as we know the cumulative distribution function, which in most cases we do, because if you have the probability density function, then the cumulative density function is just the integral of this. And I realised that unlike a lot of Wikipedia pages on things like this, there is no animation showing what it does. And I'm a big fan of animation, so if I don't see animation on Wikipedia, I sit back and think, can I make an animation that would describe the thing I'm reading well? And it turns out, yes. So if you go to Wikipedia now, you will see that I've added an animation that shows the inverse transform sampling theorem. So on the left here, it's generating uniformly distributed random numbers between 0 and 1, which again is very easy to do on a computer. It's then using the cumulative density function of some distribution, in this case a normal distribution, in order to calculate where those random numbers should end up. And as you can see, we start with uniformly distributed random numbers on the left, and by mapping with this cumulative density function, those random numbers start to form a normal distribution. So we've generated normally distributed random numbers from uniformly distributed random numbers, which I must say is very nice. Let's go ahead and see how we can actually simulate this, how we can actually generate this animation using Python. So I'll be using the Spider interactive development environment. When you download Anaconda, which is a repository of Python packages, it comes with Spider. And so if you're an undergraduate studying in a science subject or even computing, you'll probably download the Anaconda environment from package with Spider. And I like Spider because it has a nice variable explorer. And as an undergraduate, this is probably one of the first IDEs you might experience. So let's go ahead and make this animation. So the first thing we're going to want to do is we're going to want to import all the packages that are required to make it. So you see here I've imported time, because this is functions to do with time, NumPy, which is numerical Python, which includes all the things that we need, like arrays and array operations. We're going to import SciPy, because SciPy will contain the statistical functions required to generate, say, the CDF. We're also going to import matplotlib, so this will be our library that we're used for plotting. Now that again, this is probably one of the first plotting libraries that you will use when you start learning Python. And then I've got some default parameters here which make the image 8 by 8 inches with a font size of 14, so they're default parameters. The next thing we're going to want to do is define some global variables or some control variables that describe the state of our animation. So we've got our FPS, how many frames you want to draw a second. We've got numbers per draw, so this will be how many times do we sample a random number between then drawing those random numbers to the animation. So for example, 20 numbers per frame means we'll pick 20 random numbers, distribute them accordingly, and then plot the animation since those 20 random numbers were introduced. Let's go ahead and bin our data. So obviously what we saw in the animation was that the random numbers were generated and then put in bins. So the uniformly random numbers were put in bins, and then they were mapped using the CDF into the normal distribution, but they were also binned. But underlying all of that, those numbers themselves were random, and when they were mapped using the CDF, those numbers were not binned as they were mapped. They were subsequently binned afterwards, just so that we can plot them and see the underlying distribution. Go ahead and add n, which will be the total number of random numbers that we generate. So if it's n random numbers and 20 random numbers per draw, it'll be n divided by 20 total frames in our animation. And at 60 FPS, it'll be n divided by 20 divided by 60 frames of our animation. The next thing we're going to want to do is we want 4 arrays. We want an input bins, an output bins. So these are the numbers corresponding from 0 to 1, which tell you what that number should be binned into. So that's the value of the bin. And then we also want the frequencies of those bins. So the input frequencies and output frequencies. So they're all created now. You'll notice that the bins is 1 element longer. So for example, if the bins are 0 to 10, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, that's actually 11 elements. That's describing the bin edges. But when it comes to the actual contents of those bins, we only need 10 elements to describe it. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's a 0 to 1, 1 to 2, etc., 9 to 10. What we're going to do now is we're going to, like we've done in previous videos, we're just going to create a little hash box, which basically just says that this particular piece of code will be a demonstration. So we're going to demonstrate a normal distribution. We'll give a string variable called distro. So distro will literally just say this is what the distribution is. And then in order to get a normal distribution, we can do so quite easily. So you can use SciPy stats. So that has a class called a RV continuous, which will represent a distribution, which then we can call things like the PDF and CDF from. Go ahead and give the location of 0.5 because we're generating uniform random numbers between 0 and 1. So we want the peak of the normal curve to be at 0.5. We'll go ahead and give it a scale of 0.1, so nice and narrow, and then we'll close off this hash box. And this will just allow us to come back and put in another distribution to see what happens. So the remainder of this video is going to be quite simple. All we're going to do is create some random numbers between 0 and 1. We're then going to plot those random numbers on a figure on the left as they appear, and then a figure on the bottom as they appear as well, but mapped using a CDF in the middle. So for that, we're going to need to define 3 plots, but we're going to do something a bit different here. What we're going to do is we're going to implement a 9x9 grid, so using this thing called grid spec. And what grid spec does is it says that it creates space for 9x9 plots on 9x9 axes that can be inserted into the figure. And then what we're going to do is then we're going to use row span and column span, so that the central plot, which is much larger and also has a different shape, can actually span across multiple rows and columns, so that it all looks very nice. And this is opposed to using the other method where you can specify the individual ratios of heights and widths. I think this is just a bit easier. The first thing we're going to want to do is create the axis on the left. The axis on the left, as you'll see here, it's going to span from the number of rows from the beginning to 6, and then the number of columns is going to span from the beginning to 2. So maybe that's 2 of 9, and that's 6 of 9. So it's going to have an aspect ratio of 6 to 2, and it's going to represent 2/3 of the plot on the columns, on the rows, sorry, so in the y direction, and 2/9 in the x direction. So we'll see what that looks like in a moment. We're also going to remove some various ticks from, say, the top. We're going to set the y limit to be 0 to 1, because remember y now will be our uniform random numbers. We're going to set the x limit to something sensible, so we can go back and change this, but for now I've said if we have 1,000 uniform random numbers, for example, separated into 10 bins, then you would expect each bin to have an average 100 elements. But due to the random nature of things, some bins will have more, some bins will have less. So we're going to head and just make that a tiny bit bigger. We're going to remove the labels and the tick labels and the ticks. So if you go ahead and plot that, let's have a look. is pretty much what we want. We have our little plot, little axis on the left in which we can plot our little bars for our uniformly generated random numbers. We're now going to do the same, but for the bottom axis. So this will be the axis on the bottom, in which have been mapped by the CDF into their different bins. So this is almost the same, except that now the axis on the bottom, instead of spanning the first 6 rows, it's going to span the last 2 rows. But then instead of spanning the first 2 columns, it will span the last 7 columns. There's a difference here, is that we've got this thing called Diff height scale. So if you remember before, if you had 1,000 uniformly generated random numbers, the average height of each bin for 10 bins would be 100 numbers per bin. Obviously there's some error associated with the number in those bins, some fluctuation, so we give it a little bit extra. For a normal distribution, remember the peak is much taller given the same number of elements than for the uniform distribution. We need to go ahead and give it a number that describes that. We could work out the height of the normal distribution based on the formula. So there is a formula in which you can calculate the height of a normal distribution or at the mean, so the maximum height. But instead, we're just going to manually input something like 3. You can always come back and change this. Remember, this is one animation. We're not doing this necessarily to generate hundreds in a deterministic manner. We just want to generate 1. So as long as it looks good for this 1, we're fine. Let's go ahead and see what that looks like. And there we are. We'll notice as well that I've actually spanned the plot on the bottom to be 1 extra row compared to the columns on the plot on the left. And that's because I want more information here, because on the left it's quite boring just having uniformly generated numbers. On the bottom we're going to have something more interesting where we actually build up the distribution. Okay, and the last thing to add is the plot in the middle. So for the plot in the middle, we're going to get it to span between the 2 borders of the bottom plots. We're going to remove all the tick marks and set the axes appropriately. What does this look like? So this is what we get. So this is exactly what we want. We can plot our uniformly distributed random numbers on the left, get our normally distributed random numbers on the bottom, and use our CDF in the middle, which was how uniformly generated random numbers were mapped to the normally distributed random numbers. And so what we need to do now is we need to create an initial plot. So the initial plot will be, so in the middle, so axm.plot, we're going to plot the cumulative distribution function for our distribution. So we've already created our distribution. Let's go ahead and just create a mock X-ray. 1024 elements should be nice and smooth. And then we can do this. Distribution, so dist.cdf, the cumulative density function, and then we can put in our array here. When we go ahead and plot that, we see in the middle we get our cumulative distribution function, which is exactly what we wanted. What we need to do now is we need to create a container. So even though we've got no data to plot yet, we need to create a histogram, which will create just empty rectangles or rectangles with no width, no height, which then we can adjust as the numbers start to come in. And this will also allow us to plot a bit faster. For the left, we're going to do this. So we're going to create a bar chart, but we're going to create a horizontal bar chart, so bar H. So once we create our bar H, we're going to give our input bins. But remember, the input bins only go from 0 to n+1, and that's a different size to the actual input frequencies. So we're going to go from 0 to -1. So 1 less element, so we're only doing the left-hand edge. We give our input frequencies, which as you remember from the beginning is just a 0 array, so there's nothing there, so no height associated with the bar. And then the actual height of the bar in this case, so because this is a horizontal bar chart, the height is basically what you would typically call the width or the spacing between bars. We're going to set that just a tiny bit smaller, so it has a small gap in between. And then we're going to set it to align to the edge and give it a transparency of 0.5. So we can go ahead and plot that, but we won't see anything, but at least it doesn't throw errors. The next thing we need to do is we need to create the bar chart for the bottom plot. So again, it's just going to be the same code, but copied over now to reflect the fact that we're plotting on the bottom axis, and it's no longer a horizontal bar chart. We'll go ahead and give it a title. And we'll plot this title on the middle axis. We'll capture the return object, which is a text object, so we can change that. And we'll also go ahead and give the figure an overall tight layout, so that will adjust the spacing so that we maximize the amount of space our plot takes up. And now for the code that generates the animation. So we're going to need a function called update, and it will receive a variable called frame. So frame will count from 0 onwards, describing which current frame we're plotting. We're going to have a variable called redraw. Redraw will tell us whether the axis needs redrawing. And likewise, update axis will tell us whether the axis needs updating. So if you recall, we had this function where we had this variable where we said the numbers per draw. So every time a frame is requested, we're going to do 20 simulations per frame. So given that this I is the frame number, given that the frame number comes in, we just go from the current frame number to the number of frames plus the numbers per draw. And then later on, we'll make sure that the frame number that we get is incremented by this numbers per draw. This is one way of doing it. We also want to say that if I is greater than or equal to n to break, where n is the maximum number of random numbers that we're going to generate. Speaking of random numbers, let's go ahead and actually generate some. Before we step into the animation, we can say, give it a numpy.random.seed of 0. This will mean that we'll get the same random numbers. Every time we run this, and even machine to machine, you should get the same random numbers. And then we're just going to generate n lots of uniform random numbers. And if you remember, n was 50,000. So 50,000 uniform random numbers. So since we're now looping over this subset of random numbers, let's go ahead and pick out the current one. The advantage of doing this is that we can just do randos.i or randos of I to get the next random number, because frames will already step by the appropriate number of nums per draw. What we want now is we want some function that tells us which bin things belonging. This is very simple to do. So given a value in a list of bins and an array of frequencies, you can say bin value into an array. So all it does is it evaluates where the value of the bin, so the actual location of the bin, is less than the value we want. So it's basically telling you every bin that is less than the value that we're interested in is true, and every bin greater is false. If we then sum this up, it means we get the total number of bins that were smaller than our current value. If we then take 1 from this, we will get the bin to which it belongs. And then we can go ahead and actually increment the actual values of those bins at that particular point by 1. And then we can also return the index. And so now we've got our bin function, which correctly places the value into the corresponding bin and returns the index. We can go ahead and finish our update function. So we want to track the index of the left-hand plot and the index of the plot on the bottom. So we place our random number inside the input bins and increment the update frequencies and track that index. We then put the value to which has been mapped by the inverse of the CDF. So the inverse of the CDF is called the PPF, so that's the percent point function. So putting the same random number in the % function gives us the ordinate, so the value on the x-axis of the normal distribution to where that should go. We then go ahead and bin that value to the output bins, give it the output frequencies, and track the index that was accessed. We then go ahead and go over our container. So our container was what we created when we did the 2 bar charts. So what we do is the length of the container will be the same as the number of bins, -1. We can go ahead and index those containers using the index to which the values had been put in those bins. And then we can change the width of those to the new width, so the new height of the bin. We then put a bit of code here, which basically tells us that if the height of any of the bins has exceeded the current height of the window to which we're plotting, to go ahead and increase that window, or at least to tell another function that to do so. So that's where we set our update axes function. This says that an axis is updated. The reason we do this twice is because it's possible that both could update at the same time, and we only want to update the plot once. Just to speed the plot up slightly as well, go ahead and add some code to update the text. So this will set the text at the top to tell us the number of frames that have been simulated. We also need to decide what we're going to do is if the axes do need updating, we need to go ahead, reset the axis limit. So what I've done here is when a bar reaches the top of the plot window, it increases the plot window by a factor of 1.5, and it does this for both plot windows because then the bars will be the correct scales between the heights. Also going to do if redraw, so remember when we change these axes, we need to update the axes, but then we also need to redraw the plot, and then we're going to go ahead and animate. So if we look at the animation function, what we're going to do here is call this func animation. We're going to give it our figure, which we created earlier. This function update is going to be the one that does the actual frame. We're going to give it a range. So these are the frames. So it's going to go from 0 to n, so 0 to 50,000, but in steps of nums per draw, so in steps of 20. So we're going to send it 0, 19, 39, etc., etc. Because we're enabling blitzing. So blitzing means that only redraw parts of the plot which has changed. And this in general speeds up plotting, but it does mean that in our update function, we need to return a list of everything changed. Or at least what we do here is just give it a list of everything. With the advantage it doesn't have to redraw anything outside of the plot, so it should still be faster. Go ahead and give it an interval. So remember we said FPS of 60, and then we tell it not to repeat. So once it's done all 50,000 simulations, not to repeat. We'll give it just one more bit of code inside here. So what we'll say is, so if the current frame number, so this frame is divided by numbers per draw, will count from 0 to n divided by numbers per draw. It's saying that every other frame, we're going to have this condition be true, or when the frame is the very last frame, we're going to set the title of the plot, and then we're going to tell redraw equals true, which will then redraw the canvas. As we see, every other call to the plot increments this n, and we get our animation. So this is what we set out to do, to generate this lovely animation that shows how the uniformly generated random numbers can be mapped into normally distributed random numbers by using this inverse transform sampling. The last thing we want to do, in the folder where this script is kept, I've created a folder called frames. In the update function, I'm going to go ahead and implement this function, so this fig.savefig. So it will save into the folder called frames, a file called its underscore, and then it's going to get a number that goes from 0 to n divided by number of nums per draw. Going to 0 pad that to 5 figures, and then call it png. So when I go ahead and run that now, we still see the animation on screen, but now it's a bit slower. In fact, it's a lot slower. So on my particular computer, it's running about 3 frames per second. And that's because in the folder called frames, it's now generating images. Each image is a unique frame of the animation. If I just scroll down to one that's more populated, we see here, we get the individual image frames. We can then go ahead, I create a batch file, and I load in a command like this. It uses ffmpeg. I'll link a video above that will show how to create a movie from individual image frames. For the example, it will be a GIF file, but you can still use the command in the video above by just changing the output to GIF instead of all the video related parameters. But basically, uses ffmpeg, it reads the frames in at 60 frames per second. ffmpeg has been told that the names conform to this convention of 5 places padded with zeros. We then go ahead and scale it to ensure that it's 480 pixels wide, which we can change if, say, we wanted a smaller video for, say, more compatibility on Wikipedia. We tell it to use Lanczos scaling, which is a nice sharpening algorithm, which things like OBS Studio use. We then resample the frame rate to 20. So although we're reading at 60 frames a second, we only output at 20 frames a second, but there's no speeding up or slowing down. We then use this command here, split palette gen and palette use, with all the various inputs and outputs, which then generates a nice high quality GIF, and the high quality is important. Go ahead and run that. So I use Notepad++ with an extension that allows you to run code in Notepad++. And after some time, this will finish and it will output a GIF. That's completed. Let's go ahead and open it. You see we have our GIF file. So it's the same animation we've seen in Python, but created from the individual image frames into a GIF. And again, if you use the video I linked earlier, you'll be able to make movies and things out of this. But for Wikipedia, we're going with the GIF. I hope you found this video enjoyable. I know it's probably gotten quite long by now, but I think it just shows you how you can be, say, browsing Wikipedia one day, you find something very interesting and you realise there's no animation, and an animation would actually describe it really well. So you can go ahead and just use Python to actually make an animation, upload it to Wikipedia, and then everyone benefits. Hope you learned something, so thank you very much for watching.